Everyone, welcome back. Today we're going to be talking about the James Webb Space Telescope and all of the important discoveries it's made over the past half a year or so since its full functionality. So, we're going to be going over this week in astronomy as always, then we're going to talk about the James Webb. Uh, and yeah, so this week in astronomy, the James Webb Space Telescope took some really cool photos. One of them was the chemical composition of exoplanet WASP 39b. It did this looking at some of the it did this looking at some of the emission spectroscopy of the light that is being absorbed and being reflected through WASP 39b's atmosphere. And so, looking at this, we can sort of determine the chemicals that are, or the chemicals or the elements that are present in the planet's atmosphere based on how much light is being absorbed and which area on the electromagnetic spectrum it's being absorbed from. So this is what it looks like. Uh, Interestingly, WASP 39b has a lot of water and carbon dioxide present in its atmosphere, as well as oxygen, which is actually surprisingly similar to Earth. Earth also has a very high concentration of water, carbon dioxide, and oxygen in its atmosphere. However, it also has a lot of nitrogen, so that's one big difference. It also took a photo of the Able 2744 galaxy cluster. It did this looking at the galaxy cluster with a deep field using the NIRCam imaging tool. This is just what it looks like. It also took a very stunning photo of the Hourglass Nebula, which shows a protostar buried in a cloud of material that it's fueling its expansion. So that's the Hourglass Nebula. This is a very interesting case study of how solar systems and protostars come to fruition. So about the JWST, it has a primary mirror. This is the one that people are probably most familiar with when it comes to the actual telescope itself. This primary mirror is gold coated and it is um, it's incredibly lightweight. It's also thin. It has a base of carbon fiber, and it's also gold plated. One of the big reasons that they used gold for this um, was because it is extremely reflective. If you've ever seen anything made of pure gold, you'll notice that one of the most interesting capabilities of gold is its ability to sort of reflect light extremely well. So the primary mirror consists of 18 separate hexagonal segments that come together to make one gigantic 6.5 mirror long meter. Now, the reason they use hexagons is very interesting. Hexagons are one of the few shapes that have a very high surface area to volume ratio, but also are what you call mosaic, which basically means that very you can create a lot of different varieties of shapes using hexagons by piecing them together like a mosaic. And if we have a bigger diameter for our mirror, that can be achieved using a circular mirror. So obviously we can't have one giant circular mirror being sent up into space. That's obviously going to break, it's going to shatter. So we use hexagons to sort of approximate the shape of the sphere, and by doing that, we not only increase the diameter or the angular resolution of our primary mirror, but it also allows us to um, have the mirror be extremely lightweight. So this mirror is very, very big. The primary mirror has a diameter of 6.5 meters, which is huge. But it also has a secondary mirror which it reflects light back onto. Uh, so the secondary mirror receives light that is reflected by the primary mirror and then directs this light to the Webb's instruments. This mostly consists of very large, very efficient CCDs. So the spacecraft bus. The spacecraft bus is home to the six major subsystems. These are the electrical power subsystem, the attitude control subsystem, the communication subsystem, command and data handling subsystem, propulsion subsystem, and the thermal recoil subsystem. The electrical power subsystem is in charge of converting the energy from the solar panels that are located on the bottom side of the telescope into electrical energy, uh, which then is used to operate the Webb. The attitude control system is in charge of the observatory orbit and points of the observatory to the area in space that wants to be observed. As you guys may know, the James Webb Space Telescope is not actually orbiting around Earth. It's at a specific point in space called L2 or Lagrange 2, where basically the gravitational forces between the Sun and Jupiter make it tidally locked. So it has a much wider orbit around the Sun than does, say, for example, the Hubble Space Telescope. And what this allows is very little light pollution that can be coming from the Earth or from the Sun, and it also has a full 360-degree field of view at any given time. The communication subsystem, basically, it's pretty implied. It receives the commands from the operations control center and sends this to the operations control center. The command and data handling subsystem includes the CTP, which takes the commands that the communication subsystem receives and sends them to the appropriate spot or appropriate instrument in the telescope. It also includes the SSR. And finally, the propulsion subsystem contains the fuel tanks and rockets that maintain the orbits of the Webb. This is basically used for course correction if the James Webb is ever off course or is ever leaving L2. The propulsion subsystem is used to sort of keep it in place. Thermal control subsystem maintains the temperature of the spacecraft bus. All of these instruments on the Webb require an extremely low temperature. I believe it's around 5 Kelvin in order to function properly. And so space is cold, space is very cold, but it's not cold enough. So the thermal control subsystem maintains the temperature at this approximately 5 Kelvin in order to keep the telescope functional. Perhaps the most important part of the James Webb is the sun shield. Its job is to keep the infrared visible X-ray, gamma ray, UV ray radiation from the Earth, the Sun, the Moon, from reaching Webb's instruments, because that would cause a significant amount of light pollution. And this is something that a lot of the Earth-based telescopes, whether they're in orbit or on the Earth itself, suffer from. And so one of the big advantages of having the James Webb being so far away is that we can limit sort of this light pollution, and the sun shield really comes in handy for that. So let's talk about some of the instruments on the Webb itself. The ISIM is the most important piece of the telescope because it contains the scientific instruments that make the telescope function. The ISIM includes the near-infrared camera, also called NIRCam, the mid-infrared camera, also called MIRCam, the near-infrared spectrograph, which is NIRSpec, and the fine-guided system, or the infrared imager and slitless spectrograph. These are all incredibly important, which carry out very important functions in the James Webb, but perhaps the most important thing about them is that they all view um, in the infrared range of the electromagnetic spectrum. So this allows the James Webb to see a lot of redshifted light that maybe once was visible light or UV light, but because it's traveled so far in space, it's been redshifted back into the infrared spectrum. And this allows it to quote unquote look back in time because you can see the light that has come from very early on in the universe that's been redshifted into the infrared spectrum. The NIRCam is the main imager on the Webb. It's a powerful tool for studying our galaxy as well as planets. It has an infrared wavelength of 0.6 to 0.5 microns, which is incredibly small, but is still much larger compared to the nanometers or the picometers that visible light and UV light share. It's capable of detecting light from the earliest stars and galaxies, and the coronagraphs on the NIRCam work by blocking out the light from brightly lit objects so that it can retrieve images from surrounding objects that are more faint. Solar panels This is pretty self-explanatory. This is located on the lower side of the spacecraft bus, and they convert the sunlight hitting the telescope into power that is used to operate the instruments on the telescope, as well as all of its subsystems. That's basically it. That's all for the JWST. Thank you for listening, everyone, and I'll see you later.